Hello everyone, my name is André Martins, I came from Leiria, Portugal, and today I will talk about the work entitled An Approach to Integrating Manufacturing Data from Legacy Injection Molding Machines using OPC UA. This work was developed under my PhD studies with my colleague Bruno Silva and my supervisors, Professors Hugo Costelha, Carlos Neves, Sean Lyons and Sean Cusgrove. I hope you enjoy it. This is how I will proceed with the presentation today. I will start doing the contextualization of our work and talk about our motivation to do it. After this, I will talk about other authors' work related to this topic. Then, I will present the developed integration system and the scenarios used to test it. At the end, I will talk about the test results of our work, the conclusions, and also future developments on this topic. To achieve the ambitions related with the concept of a smart factory, manufacturers of new industrial devices have been developing and releasing products capable of integrating themselves into fully connected environments. In these environments, the automatic retrieval of data across the shop floor is a must, allowing the analysis of machine performance for increased production quality and output. On most of the recently released industrial devices, this machine data is readily available. However, the same is not true when using legacy devices. It is also true that most SMEs are unable or do not intend to radically replace their industrial devices with this purpose only, since that would imply a high investment and mainly because many of these legacy machines remain highly productive. That said, there is a need to develop integration methodologies for these legacy industrial devices and provide them with smart factory communication capabilities that make them suitable for the factories of the future. There are several works available regarding monetization and optimization of the injection molding process. For instance, the one developed by Kittonen and the one by Jung use production and process data from the injection process to feed machine learning algorithms with the aim to generate fault alerts and predict machine events. Other works, like the one by Obregon, provides a rule-based explanation approach that supports operators and managers to visually and easily understand the most important manufacturing process parameter that influence the production process. The data supplied to this machine learning algorithm is collected during the injection process through several sensors installed in the machine. In our approach, in order to keep the costs and system complexity low, the priority is given to the collection and manipulation of data already available by the machine controller. Other example is the work of Trifati that analyzed production data from an injection molding process containing around 70 process variables from different machines. Here, the raw data was collected from these machines and recorded during the production process. The analysis mentioned on this paper was performed in the end of the injection process, while in our approach the goal is to have this data readily available in real time at each injection cycle. The most relevant work that influenced the work presented here today is the one published early this year by my colleague Bruno Silva. His work covers the data collection, treatment, storage, and monitoring process, but without making the data available using a standard approach. The work presented here today intends to solve this gap, developing an integration system for legacy injection machines based on OPC UA technology. The main supporting technology of the developed work is the OPC UA standard. OPC UA is a standard that, due to its characteristics, ensures the open connectivity, interoperability, security, scalability, and reliability of industrial devices and systems. Based on a service-oriented architecture, OPC UA is much more than a protocol. It has built-in information models and defines basic rules for information exchange. The standard information model is designed to allow type definition so that designers can meet their own application needs, and on top of this, information models can also be combined for specific areas such as in this case, injection molding machines. These specific models are called combining specifications and derive from the standard OPC UA data types. In order to define the information model of our OPC UA server, the Euromap 77 combining specification released by VDMA and OPC Foundation in 2019 were considered, specifically following the information model example for this purpose. The hierarchically structured address space built by the OPC UA server for the Negri-Bossi machine, as an example, was explored, as you can see in the figure on the left, by a generic OPC UA client interface called UI Expert. Here you can see the overall architecture of the developed system. The information flow starts on the legacy injection molding machine block that represents the legacy machines able to generate files containing data about the injection process. Other submodels, such as the power meter and interface models for external sensors data acquisition through protocols such as Modbus TCP, are not in the scope of this work, although it is possible to integrate this data in the created OPC UA server address space. The information block on the middle represents the experimental system developed in the scope of this work, based on a single board computer that emulates a mass storage device through its USB on-the-go port, while at the same time running an OPC UA server that can be accessed by an internet connection. The connection to this server by OPC UA clients allows accessing the OPC UA variables containing the mapped injection process data from machine files. Regarding open connectivity, unlike OPC Classic, OPC UA supports multiple operating systems, allowing to run our OPC UA applications in Linux-based ones. This characteristic allowed us to use an open-source single-board computer named Orange Pi 0, running a specially adapted Linux distribution called Armbian. This specific board was selected mainly due to three characteristics. USB on the go. This functionality is used here to emulate a mass storage device that will be used by the injection machine to store the data file containing information about the injection process. LAN ports. Recently released equipment that have built-in OPC UA communication usually have LAN ports for making it accessible via Internet interface. Low cost. This single-board computer costs around €20. Keeping the investment low can contribute to an increasing adoption of such integration technologies, allowing even SMEs to convert legacy machines in smart factory compatible devices. Regarding the OPC UA server development, the open source C library containing implementations of OPC UA servers was employed. The developed system was tested with three different file structures, generated by three different legacy injection machines in industrial environment operation. The Negri-Bossi machine generates a text file whose name can be configured in the injection machine controller interface. It has a limitation of 6 variables registered in the file at a time, so they need to be selected in the machine controller from a list of available variables before the injection process starts. The structure of such file can be observed in the figure, showing in the first 8 rows the file header information and in the last 4 rows the data generated by 4 completed injection cycles. Each new completed injection cycle generates one line with information about that cycle, which is appended to the end of the file. For this specific machine, tests were performed on an industrial environment during an injection process. In this figure, the data access view from the UI Expert client was used, allowing us to observe those variables as well as their last values, matching the values from the last row of the process data file. Concerning the process data files generated by the Angle 600 machine, their structure can be observed in the figure. The first 22 rows contain the file header information, and the last 4 rows show the data generated by 4 completed injection cycles. The files generated by this machine have the CSV file extension. Similarly to the previous machine, each new completed injection cycle generates a line with information about that cycle that is appended to the end of the file. The first 8 rows of the header describe the model and the name of the machine, date and time, number of the attached mold, and material in use. From row 10 to 19, a list of variables, labels, and their corresponding abbreviation version is observed. Line 21 contains the abbreviated version of the labels and their corresponding units. The tests with this machine were carried in a laboratory environment, although using files generated from real machines during injection process in industrial scenarios. Regarding the process data files generated by the Tedric injection machine, they have the text file extension, whose structure is shown in the figure. The first 4 rows, similarly to the previous machines, represent the file header, containing machine model, date and time information, variables labels, and their corresponding units. The last 4 rows represent the completed injection cycles information. Similarly, with the Angle machine, the tests with this machine were carried in a laboratory environment, although using files generated from real machines during injection process in industrial scenarios. Now let's talk about conclusions and future developments. So, legacy industrial equipment does not provide the intelligence needed for smart factory connectivity, making its integration on these environments important, given that these are still being highly productive for the main purpose they were built for. The presented system parses text files generated by the machines and maps them to the structured address space from an OPC UA server built with the Euromap specifications, revealing to be capable of providing a standardized approach for injection molding machines. There are a wide range of legacy injection machine models available across the factory's shop floors, with different characteristics and different ways of making the injection process data available. The presented tests on this work shows the feasibility of such data integration, gathering the information from 3 different legacy injection molding machines within the same application. Future work in this topic will include the creation of a runtime configuration interface that allows to, from a list of supported injection machines, select the one we want to collect data from without the need to recompile the code every time. Incorporation of file header information, using it to set OPC UA properties. Also, the natural evolution of this application includes supporting a broader range of injection molding machine models as well as other peripheral equipment commonly used in injection process. Thank you all for your attention. If you have any questions, please let me know. You can use the conference platform or just email us.